Thank you. Yeah, so IPAM is about connections between mathematics, branches of mathematics and computer science, physics, other fields. And so I approach this topic, open quantum systems, from a computer science background. And being the first speaker, I thought that I would give a bit of a historic overview and then also some technical introduction to these things. So several of you might have heard the first half of this talk. In the second half, we will also speak some recent developments in this topic. So the history of this Metropolis-Hastings algorithms, which is like a classical analog with this open quantum system dynamics, is very fascinating. And it was invented in the late 90s by Stanislav Ulam, who worked together with John von Neumann, trying to tackle challenging problems in computation, for example, related to atomic bomb and hydrogen bomb and so on. And they're working at Los Alamos, and this code name Monte Carlo was a secret computational project, and this was suggested by their colleague who built these first classical computers, and was in reference to Ulam's uncle, who was often gambling, even in Las Vegas, apparently. And the foundational paper of this topic is by Metropolis, Arianna and Marshall Rosenbluth, Augusta and Edward Teller, who developed an algorithm for studying chemical physics problems to thermodynamical averages. And the Los Alamos project brought wives and husbands working closely together, so that's maybe one of the reasons behind this unusual set of authors. And apparently, Metropolis just built a computer. We know very well how hard is it to build a new paradigm computer, so it was a hard work, definitely. And this was originally developed for the set problem, but it turns out that it's very useful, this approach, for other complex systems as well. And there was some interesting mathematical generalization to this idea by Wilfrid K. Hastings in 1970, and that's why it's now known as the Metropolis-Hastings algorithm. And just to demonstrate the significance, it was actually named as one of the 10 most important algorithms of the 20th century. So here is an idea in terms of computer science language. Suppose we have some regular graph, such as the hypercube, and a simple random walk will converge to uniform distribution. It's easy to see. If you just randomly choose where to go, you will end up at a random position uniformly. Now, what if we want to sample from different target distribution, something which is like proportional to weighing 1, 2, 2, 4 the vertices? Well, then on the left-hand side, there is the original uniform random walk. On the right-hand side is the modification, where we modify transitions. If we are moving to a more likely position, then we just keep the transition. However, if we move to a less likely position, so this is a more likely one, we are moving to this less likely one, then we are just reweighing the transition by the ratio of these probabilities. And then, it will converge to the target distribution that we were hoping to achieve. And so mathematically speaking, it can be expressed as that this modified reweighed walk is detailed balance with respect to this target distribution. And it means that the probability exchange between any two nodes is 0 in expectation. So the Metropolis algorithm is in general that we want to make a transition from x to y. And as I said, if we are moving to more likely place, accept it. Otherwise, only accept it with probability, which is reweighed by the ratio of probabilities. And this is the detailed balance condition. It just really means that, I am less likely to be here, but more likely to do a transition, versus I am more likely to be here, but less likely to do the transition. So in general, the probability mass exchange is equal between pairs. That means that in this target distribution, I don't change the current distribution, and so this is a fixed point where the walk will converge. And so this is really the general idea. To put it in a way that relates more closely to the physics picture, let's talk about Gibbs sampling and talk about this target distribution as a Gibbs state for some Hamiltonian. And now we can take a classical Hamiltonian. This is really just assigning some energy value to classical strings, spin strings, something related to pairs of strings and also maybe some individual potential. And this describes my energy landscape, and the Gibbs state is just the exponentiation with the corresponding inverse temperature beta. And in this case, if I have n spins, little n spins, then I have 2 to the n configurations altogether of these spins. And so if we want to do this Metropolis algorithm, we are building upon a symmetric exploratory Markov chain with some transition matrix, and it has non-negative matrix elements because it's some probability transitions. And very simple example is just picking a random spin and flipping it. And this is exactly the random walk on the hypercube that I told you, just in different language. And the Metropolis algorithm will make these transitions, but reweigh them, as I told you already, and it will be detail balanced. And if we want to actually translate it to a stochastic process, then we can we can take a continuous time Markov chain where with this generator, where from the transitions we need to also subtract the decay, and that is just how much in total we are jumping away, at what rate are we jumping away from an individual configuration. And so this is needed for preserving the probability mass altogether. So these are the jumps, and these are corresponding to decay. And if I'm just exponentiating that, I'm going to get a continuous time classical Markov chain. But I can also convert it to discrete time dynamics if I add identity to this generator and things are sufficiently normalized that it's going to be a stochastic matrix, and I can just iterate that. So the continuous and the classic and the discrete setting are very, very similar, just a slightly different way of taking powers and exponentialization. So what is required for this algorithm to work? Need some way to reweigh these transitions. It turns out, it turns out that in general, the only thing is required that if I am looking at the transitions and I am applying some weighing function, then this weighing function that weighs one versus the other direction of the transitions should satisfy this equality. So if there is some ratio of probabilities, then this gamma of the ratio should be the ratio times gamma 1 over the ratio. And this will always satisfy detail balance. It's not difficult to, to see. And so one such function is this Metropolis algorithm that I told you, that is always accepting the move to the more likely place and only accepts with the ratio of the probabilities if it's moving to less likely. But there is a more smooth version of this rule, and that's given by this Glauber rule and leads to Glauber dynamics. Sometimes it's preferred by pure mathematicians. And this is just another function which is kind of smoothly approximating this Metropolis weights, but also satisfies this relation, so it will be also detailed balanced and converge to the target distribution we want. And okay, so this is just a really simple proof of this fact that this leads to detailed balanced dynamics. So this is the reweighing function for one way of the ratio, it's the other way of the ratio, and I start from this distribution, make the transitions, and this is my new transition rate, or transition rate, and I'm just rearranging, and it turns out that this is going to be equal, the probability mass exchange is exactly equal if and only if my function satisfies this relation. So really Metropolis and Glauber are pretty much the same, just this tiny detail of how you exactly weigh the transitions back and forth is the difference. And then this above equation just ensures that the probability mass exchange is equal in both directions, so we are converging to the state that we want, well, unless there is some separation of the space to pieces where we only that disconnects parts. But if I have a graph which is connected, then it will always actually follow to this unique fixed point. And okay, so this is a very intuitive way of looking at detail balance, probability mass exchange between two pairs of nodes. But I can also describe it in terms of linear algebra. So if I just take these transitions and I multiply with the diagonal matrix with the target distribution on the diagonal, then it should equal the same when I multiply from the left. And this is just expressing this pairwise relationship in a single matrix equation. But this is more linear algebraic. And then I can also symmetrize this expression by just multiplying by square root of this tau inverse from both sides. And I get this equation. And what it means, now you can realize that the left-hand side is exactly the transpose of the right-hand side. So it just means that this particular varying of the transitions is a symmetric matrix. And well, this is going to be more quantum friendly because in quantum friendly, in the quantum case, it's harder to identify what's a node. Like this graph is more fuzzy in the quantum case, but this is just some linear algebra notion, and I can work with that in a quantum case. So that brings us to stochastic quantum transitions. And so the quantum Markov chain or quantum channel is a completely positive and trace-preserving map that is the most general form of quantum transformation that is allowed in quantum physics. And so complete positivity means that if I have a density operator, then it looks in this way that I have some set of so-called Kraus operators, and I just sandwich this row from left and right with these operators, and that is a completely positive map. All completely positive maps can be written in that form. And trace preservation means this particular relation in terms of the Kraus operators, and it just means that if I put in a unit trace row, then I get out a unit trace sigma. And okay, so this is the kind of the discrete time analog of a Markov chain in a quantum setting, but I can also work in continuous time, which is often much nicer analytically. And then the same thing happens, I just have to exponentiate some appropriate operator, well, or superoperator in this case, which is called the Lindbladian. And it looks similar in the structure for a quantum channel. It has some transitions. It is a completely positive map. Then it has some decay, which makes up for the change that I am moving away from a position and I'm no longer there. So it just ensures trace preservation. And there is an additional coherent term, which is not there in the classical situation. It just, if I only had this term, that would be just the Schrödinger equation. So I can, in this picture, seamlessly combine coherent evolution like Heisenberg and randomized jumps. And this is what happens in continuous time. This is a Lindbladian. And so later on, I will just write it in this transition part and decay term. Turns out that this can be expressed as T-dagger identity, this decay time, and the coherent term. And so I will focus on this detailed balance in the KMS form. And well, this is just this self-adjoint relation. If I'm taking my superoperator, I'm sandwiching with square root from left and right. Well, but what does it mean to sandwich with square root of the operator? Well, I can actually put these powers in different settings, but this is the most symmetric, the KMS. So it's instead of putting a square root just on the left-hand side, it is symmetrically sandwiching it from right and left with this 1/4 power, and it's inverse from the outside. This is exactly the quantum analog of the previous classical detailed balance equation in terms of these linear algebra terms. And so suppose that I have a Gibbs state in mind, that I want detailed balance dynamics with respect to this Gibbs state. It turns out that this Lindbladian will be detailed balanced if and only if the transitions are detailed balanced. And there's an additional condition that, that the coherent term has to look as some sort of transformation of the decay part. So the decay is telling you how much you go away from different places, and it has to be like that. In particular, if the decay term commutes with the target state, then the coherent term is 0. So then you get back more close situation to the classical one. But if this decay term does not commute with the target distribution rho, then there has to be some coherent term. that makes the whole transformation detailed balanced. This is a stark difference with the classical situation. Okay, so why do we like this KMS detailed balance? Well, classical detailed balance is very useful because it's a very intuitive notion and enables us to describe fixed points which are otherwise hard to engineer. And it's easy to express in terms of this symmetricity of the transitions. And as I showed you, this is the quantum generalization in the previous slide. So it just means that I have a self-adjoint superoperator after some reweighing. And well, the proof that if you have seen it and you know it's extremely simple, it's just one line to prove that if you have detailed balanced transitions, then actually the Gibbs state is a fixed point. It's just really a single line proof that uses detailed balance. In this middle equation, I am just doing some rearrangement that is expressing the detailed balance condition. So L is describing transitions, and if I have basically no change in my state, this is like the derivative of my state. If the derivative is 0, it means I don't change, so rho is a fixed point, and this just follows from detailed balance. So it's very easy to work with this detailed balance in some settings. And it's very desirable for that reason. But there is a major issue in how to handle the ambiguity in phase estimation because, well, you remember the Metropolis rule originally wanted to know about the ratio of the likelihood of different positions, and well, that would be just basically ratio of energies in the Gibbs sampling setting. But because of non-commutativity, learning the energy of a state may be very difficult in the quantum setting. In the classical case, we had just bit strings, we had this simple spin Hamiltonian, and you could just easily compute what is the energy of a single state. In the quantum setting, we have non-commuting Hamiltonians, and given a quantum state, it's not so easy to determine what's the energy of it. And so there were some ideas on how to attack it using a shift invariant or perfect phase estimation, but that's unphysical in most situations, so it doesn't solve the general case. And then there was some very good ideas about how to overcome some difficulties in the discrete setting by using a continuous time version of these dynamics, but still required some sort of rounding promise that made it also a bit hard to apply in general case. And then there were some ideas on how to actually fix this rounding promise by some randomized process. So this gives you one way of tackling this issue, but it unfortunately led to large overheads. And there turns out to be a better way of doing this that I worked with some wonderful co-authors on. And this followed up on this idea of doing this dynamics in continuous time and using some smooth variant of approximate phase estimation. And it required no extra conditions, so it was actually generally applicable and required and had an efficient implementation. But the jumps, unfortunately, in this non-commutative setting are non-local, and the detailed balance was only approximate. But, this upcoming is no longer true. We have proved it. So actually, these detailed balance transitions can be made exact, and that is exactly based on this correct form of this coherent term that I described in the previous slides. And the idea is, once again, just apply this damped phase estimation, which is somehow estimating energies with Gaussian uncertainties, which we call the operator Fourier transform, and then also needs to add this coherent term that I talked about. And so this was the first variant with Anthony, Michael, and myself, this idea of operator Fourier transform. And this was nice because it gave rise to quasi-local transitions. They were not fully local, but at least quasi-local, meaning that they had like exponential decaying tails in the longer distances, and detailed balance was exact. And there is a new construction, well, new, maybe that's a bit of overstatement now, but not that old, from 24 by group led by Lin and also myself. Basically the same construction put in a slightly different context or language. And then a major difference is that we just somehow filter the jumps themselves in some weighted integral over Heisenberg evolution. There is no direct operator Fourier transform. We never actually estimate energies in this picture. That's different in the setting. We learn less about the system. So constructing detail balanced dynamics is done by this detail balanced route. And how is it achieved? Now we have several ways, and I just want to put a common view of them. So the good thing is that we have linear constructions, and it means that we can just look at the level of individual Kraus operators. So Kraus operators make up my transition part, and since my construction is linear in terms of superoperators, I can just look at Kraus operators one by one. And so the Davis Metropolis approach would be basically do the classical metropolis in the eigenbasis. And that's very much a classical approach, but it's discontinuous because it can distinguish very small energy differences, and that's non-physical. And now a newer way of doing this is this operator Fourier transform, which is approximating energies in a more smooth way, and that can be made work, as we showed. It has actually been, this is the archive date, but it has been published in Nature a few months ago. And here the idea is that we are decomposing the jump operators, these Kraus operators, in this weighted Heisenberg evolution, and it basically, this k omega will be a rough, it's a decomposition of the Kraus operators, and these labels tell you roughly how much they change the energy up to some Gaussian uncertainty. And this is done by this integral, this Gaussian uncertainty. This ft would be a Gaussian function. And then the entire map would be just using these uncertain jumps with labels. And according to the label, just apply this weight function as in the Metropolis setting. But it turns out if you assume that your estimation was off by a constant, depending on the width of your Gaussian, actually this will be detail balanced. So do the same thing as if you would have exact estimates of energy differences, just add some constant amount to shift due to uncertainty, and it will check. It's kind of magical, but this is a nice proof that it works like this exactly. So somehow, because of the nice properties of Gaussian distributions, you can exactly counteract these uncertainty issues. And actually it turns out that it was known in the classical literature that this helps in uncertain situations, but of course the quantum case is more general, so we need a bit more work to do that. And another approach is, that is the newer one, it's using coherent reweighing, and that just keeps the jump operators intact. So one jump operator gets mapped to a new single jump operator. Here a jump operator was mapped to many jump operators with different labels. Here it's kept in a single one, but the different parts are reweighed. So in particular, this energy transition that is moving from energy eigenstate psi to psi prime, it's reweighed by, again, this Glauber-like function. And the key difference is that it's just reweighing a part of an operator, but the operator remains a single jump operator, just different parts are reweighed by different numbers. And the very nice thing about this, that if you look at this in the eigenbasis, this looks like something very complicated. I told that even estimating energies are very difficult in the quantum setting. However, this reweighing can be expressed once again as a weighted integral over Heisenberg evolution of these jump operators, and that's something that you can implement on a quantum computer, and it's a continuous operation, continuously changes it depends continuously on the Hamiltonian, unlike this classical Metropolis eigenbasis type approach. And yeah, so this function is some exponential decaying function that basically means that you only need to worry about limited time Heisenberg evolutions. And just a high-level overview of the different approaches. So the question is, what do we or the environment learn about the quantum state while this process is performed when a jump is made? And in terms of Davies, then the exact energy difference caused by the jump is learned. That's a lot of information. And that's why the corresponding quantum algorithm will be totally, like, fully non-local, entirely global operation. So phase estimation-based Metropolis only learns approximate energies before and after the jump, so it's already slightly less information. An operator for transform is difference that it only learns energy differences, not jumps before and after. No, not energy before and after, so this is like two numbers, energy before, energy after, and this is one number, energy difference. That's already less information. And the newest of these approaches learns actually nothing about energies because it just transforms the jump operators and then applies them to the state. So this is the one which learns the less about the quantum system, which has its ups and downs, but it's interesting that in somehow the history of these quantum algorithms, we went from full knowledge to basically no knowledge, and that's the most state-of-the-art approach. And okay, so the one other important consequence of this detailed balance story is that you can turn this Lindbladian to a self-adjoint operator. Well, what are self-adjoint operators in quantum mechanics? For example, Hamiltonians are self-adjoint. So I can think about this symmetrized version of my Lindbladian as a sort of a parent Hamiltonian. And I'm just taking my Lindbladian, and I'm grouping together these decay and coherent terms in a particular way. Then I get a parent Hamiltonian construction that just takes these decay and coherent terms and these jump operators and creates a Hamiltonian, a Hermitian matrix on a doubled system, where your system size was, say, dimension d, then this is 2D by d matrices tensor producted, so it's a d square dimensional system now. And the symmetrization that is needed in this detailed balance condition is applied to the jumps. And so this is the definition of this parent Hamiltonian, and the nice thing is that this canonical purification of the Gibbs state is guaranteed to be the ground state. This is corresponding to the fact that the Gibbs state is a fixed point. And so now this kind of gives us access to a pure version of the Gibbs state. And now it's a frustration-free quasi-local Hamiltonian that we have at hand, and that has a huge literature, and this gives us many tools from the study of these quasi-local frustration-free Hamiltonians, so we can import a lot of results from there through this connection. And yeah, so I'm describing it in terms of Lindbladians, but you can also do the same story for quantum channels. That's no difference there. And okay, I wanted to say a few words about implementation. So once again, the key constructions can be expressed as a limited time Heisenberg evolution weighted by some appropriate function. And so this transformation is key at these constructions. This is S plus minus. It just takes the operator and subtracts or adds this S operation. And S is just this form, this integral. And this is how I obtain my new jump operators. And because it is exponentially decaying function is f, due to Lieb-Robinson bounds, I know that these resulting operators are quasi-local, and the locality radius will be beta, the inverse energy. And this works when K and the original system Hamiltonian were both local. And so we are still trying to find what is the most practical version of this group of algorithms. In classical situation, people often like working with continuous time for theory, but discrete time for practical applications. So we were wondering how to how to make this process inherently a discrete time algorithm. And so the idea was that instead of looking Lindbladian simulation with this continuous time dynamics, we could maybe just make these transitions into a quantum channel by adding some decay term in a discrete setting. And this can indeed be done. We showed that there is a appropriately defined single Kraus operator which you can add on top of your normalized transitions, and you obtain actually a quantum channel. And that's going to detail balanced, and this K, this extra operator, can be expressed analytically, and it will be once again quasi-local and have all the nice properties that we wanted. And so, yeah, this is the analytical form. The key thing is that we can, we do have its matrix value Taylor series, although it's a kind of ugly looking expression and it's quasi-local, but maybe this is still not the most practical thing to do in the classical, in the actual implementation. So we try to push it and do an iterative version of it, which is not so ugly, but still preserves the advantages of discrete time algorithm. Well, I will maybe say a few words about that in the next slide. But I just wanted to summarize this rough overview before I tell you a bit more about our recent results. So this is like a summary of classical and quantum analogs of these Glauber and Metropolis dynamics, and what do we know about them, what are their key properties. So Glauber and Metropolis dynamics is efficiently implementable, local, zero energy uncertainty. We know everything about our states. It's ergodicity preserving, which means that if we start with an exploratory process that is exploring the entire space, then it's going to converge to a unique fixed point. And the Kraus rank, so the number of jumps, doesn't change or doesn't increase. So everything is perfect in the classical situation. In the quantum situation, more complications arise, but while we approach almost the same guarantees as in the classical situation at the end. So the Davis generator is not efficiently implementable, not local, and it has various problems because of this zero energy uncertainty, which is unphysical and can increase the rank of Kraus operator and so on. Phase estimation has similar problems, but if we add this Gaussian uncertainty, that we can at least implement it efficiently. Now, operator Fourier transform, which only estimates energy differences, it gains us quasi-locality, so it makes from these non-local transitions to actually quasi-local transitions. And then we have the last version, the coherent reweighing. Well, it doesn't learn anything about energy, and as a result, it doesn't increase the Kraus rank. And well, most likely it will also keep the fully connected exploratory chain. It will convert it to a unique fixed point quantum channel or Lindbladian. And so this is just really a view of these exact detail balanced channels. And in the recent years, there have been many different works over approximate versions, too many of them to list on a single slide. So I just focus on the exact versions. And maybe they will be actually more practical at the end. But from a theory perspective, it's appealing to have also this progress towards more practical things while you stick to your high standards in full detail balance and very nice theoretical connections. And okay, so here is the new discrete version that I talked about, which instead of doing this very complicated matrix value Taylor sequence, it just basically looks at the first order approximation. It just takes one jump operator and one decay term and applies some relatively simple transformation and defines the next level of addition. So as opposed to giving a single Kraus operator that makes up for trace preservation by keeping detail balance, we add the sequence of Kraus operators. But this sequence of Kraus operators is converging double exponentially to the desired map. And it's a very simple iteration every step. So we don't need to add many maybe 3, 4, 5 would suffice in practice, and we actually have a quantum channel. And so this is our candidate for making this theoretically clean approach efficiently implementable. And we even have some resource estimates for the Heisenberg XXZ model at various target precisions, how to implement this key step, this S transformation in the jump operators for this Heisenberg XXZ model, an L by L lattice. And so this is L, this is the target estimation accuracy, and then what is the inverse temperature. And the numbers don't look crazy. We still need a bit of work to put them into full end-to-end context. It's work in progress. My student Csaba is working on this actively. But the upshot is that the numbers don't look that bad. So especially if you compare it to some quantum chemistry algorithms, then this 10 to 8 is actually a moderate number.
So which approximate version of the algorithm are you using?
So this is using this is just using the S transformation, and then, depending on like what level you truncate, for example, your Kraus operators, maybe you need like 4 iteration of that or something. And that will be like a single step of your discrete time quantum channel. But yeah, there is I guess more details will come out in a paper soon. Hopefully February we will have it out.
And this is the it got per unit time.
Yeah, so this would be a quantum channel. So you iterate it, it's discrete, so this would be basically what you need to do for implementing a single step of your quantum channel.
So it's not per unit time. So from a continuous time perspective, right?
No,
so
this is a discrete time perspective. So
which means there is a time step.
Yeah, there is a time step. This is per unit time step, unit time step.
Unit time step.
Yeah, exactly. Okay, and then, one important question is, one important question that I glimpse some light on it is, what is the cost of a unit time step? And the other question is, how many steps do you need to converge to the Gibbs state? Because once you have the Gibbs state, you can just analyze it, take observation values, whatever you need. And here, once again, analyzing how many steps you need, detail balance is coming handy, because your Lindbladian can be converted to this parent Hamiltonian, and it's the gap of this parent Hamiltonian tells you the mixing time, roughly up to some minor additional factors. And one advantage of this new approach that is keeping number of Kraus operators, that it's a bit easier to handle in a classical simulation setting. So, of course, we will want to run these algorithms on a quantum computer, but we want to understand in reasonable sizes how they behave. And for that, classical simulation is more useful, because we can just stop a classical simulation and look at what's at the memory at this point and examine, which is much more complicated in terms of a quantum computer. Quantum computer stores a quantum state. Even learning what is that quantum state requires tomography and a huge headache. So as big as we can, we want classical simulation to understand the behavior and the main effects, and then only the larger sizes on a quantum computer. So my other student, Balázs, who is also sitting here, developed some special purpose tensor network simulations for this problem, and they verified it with exact diagonalization for small systems, just to make sure that everything matches up. And they looked at the Transverse-field Ising model and also the Heisenberg XXZ model at various temperatures to see how big is this Lindbladian gap. So, and the inverse of that is approximately the mixing time. And so here are their numerical results, tensor networks all the way through, and then exact diagonalization in the boxes, showing you the Lindbladian gap. And well, it's 1D systems now. Well, we know that for 1D systems there is a gap, but this gap is reasonably large, even at relatively higher temperatures and values of system parameters. So we see that with system size they converge, and they converge to a reasonably large value, not just an extremely small constant that the theory would give you. And similar nice results were obtained for this XXZ model. So this is, yeah. And what is the Lindbladian that we started with? Sorry, I didn't say much about that. So basically, the exploratory chain is just as told you in the hypercube setting. Pick a random spin and flip it. And how do you flip it? In quantum setting, you have three different ways of flipping a qubit via X, Y, or Z operation, and you just choose randomly. This is your exploratory chain, and then you use the transformation to make a detailed balance with respect to the Gibbs state, and then that's Lindbladian, and here is its gap. It works nicely, so we are hopeful that maybe in 2D we will have some nice results, but it's much more challenging to attack tensor networks, so it's still work in progress.
Sorry, one question.
Yes?
Did you also look at the scaling in terms of beta of the spectral gap in this case?
Yes, we do, but somehow I think it's only one beta in this image. Yeah, they don't go to crazy low. I mean, it's with larger beta, the tensor network algorithms also getting more difficult because the quasi-locality is increasing and everything is more difficult. But for the beta values, I think up to something like 2, 4, it was looking promising. But this is also work in progress. Yeah, we plan to also maybe, publish it in the first quarter of this year. The numerical paper about this. And okay, finally, I wanted to also mention a third direction of research, so not just resource estimation, not just estimating the gap with numerical methods, but also maybe some analytical ways of bounding the gaps, and that is through Cheeger inequalities that I'm working on currently with Umesh Vazirani. And so I can tell you this result that we have, and we are still working on some more generalizations of this. So the Cheeger inequality in the classical computer science tells you that if some random walk mixes slowly, that the reason for that is that there must be some bad cut. So there is no bad cut, then you mix fast. If you mix slowly, then there must be some bad cut, which basically a separation of nodes that very few edges go between them, and so mixing is bottlenecked. So if we have a self-adjoint Lindbladian, then we can show this quantum version of this Cheeger inequality, which tells you that the gap of your Lindbladian, so the spectrum will be negative, so the largest non-zero eigenvalue is a negative number, and I have to put a minus sign here for that reason. So this gap up to a quadratic factor is determined by the worst cut. So I just look at subspaces of my entire vector space and look at orthogonal projectors, pi s. And so these are the transitions that my Lindbladian makes. And so how much transitions help getting outside of this subspace is measured by this. You take your transitions for the subspace pi s, and you look at how much it went outside. So this is the orthogonal projection, and you take the trace. This is a measure of how much communication is in between the subspace and its orthogonal complement through the transitions. And you divide it by the minimum of the dimension of S or S complement to make it properly weighed. This is exactly the quantum analog of the analogous classical Cheeger inequality, and we have it in this case. And well, people, including Kristen, who is also here, looked at this problem already almost 2 decades ago. And they had already a quantum Cheeger, but that only applied in their setting to symmetrized versions of unital channels. So this is a direct generalization of their results, and we are trying to generalize it even further to cases where you have this detail balance, KMS detail balance with respect to different distributions, but that's more challenging because of non-commutative effects. So we are still working on that. And so some open questions, and well, I will just list some important work. When I first made this slide about 2 years ago, then it was much fewer, and there is now not enough space to list all of the results, so I'm sorry if I missed something. I'm just trying to put some historical highlights. So we know that high temperature lattice Hamiltonians are rapidly mixing. And we know that random sparse Hamiltonians at fixed temperature are also rapidly mixing, so we know that the gap will be large, and even more rapidly mixing. If we have some Hamiltonian which satisfies this physically motivated eigenstate thermalization hypothesis, kind of random enough from some perspective, then we know that it's also mixing fast. And we have also results about perturbed free fermion models, and well, promising simulation results in quantum chemistry, and also some interesting bottleneck analysis, finding causes for slow mixing, which is very much in the spirit of this Cheeger inequality that I told you, but only one direction, the slow mixing reasons. And one highlight from last year is that quantum spin chains thermalize at all temperatures. Both authors will attend this workshop as well. And some more general questions is how noise resilient are these algorithms. They are open system algorithms, so they kind of work with noise, but they work with engineered noise. So how can we deal with non-engineered noise? Ground state preparation is at the edge of these Gibbs sampling techniques, and I don't know, maybe Lin will talk about this in his next talk. And a very annoying theoretical question at the end is this secondary type quadratic gap amplification for these parent Hamiltonians or discriminants. That's another name of the same concept. And the only known construction where this can be made working in the quantum setting is for approximate detail balance variance, coming from Kristan's and Pavel's paper and our follow-up. But we don't have a version where you get this quadratic speed up and you have exact detail balance, and for annoying technical reasons. So I don't know if this can be overcome. This is, I think, a major theoretical open question. And so, as I showed you, we and many people and most people in this room are working hard on making progress in terms of numerical understanding, theoretical understanding, different generalizations, implementations, resource estimation. A lot is going on. And the good thing is that I got some nice funding for all these questions for the upcoming 5-6 years. So I got an ERC grant, have some Marie Curie Fellowship open. I'm also working on an X Prize entry that's a competition for quantum applications. And so we need more people doing Gibbs sampling. And if you're actually interested in maybe visiting or coming to Budapest and Europe, then please talk to me. Thank you.